Okay, 3.14, pretty simple problem overall. Basically just prove a bunch of different operators or operator equations. So let's start with the first one, which is we want to prove that the commutator of a hat plus b hat with c hat is equal to the commutator of a hat and c hat plus the commutator of b hat c hat. So if we write this out fully, right, a hat, whoops, what is going on with my pen? There we go, a hat plus b hat with c hat can be written out in full as a hat plus b hat c hat operating on f subtracted by c hat a hat plus b hat operating on f. And operators aren't commutative, but they are still distributive, so this can be written out as a hat c hat operating on f plus b hat c hat operating on f minus c hat a hat operating on f plus c hat b hat operating on f, in which case, if we rewrite this, this is a hat c hat f minus c hat a hat f, where I'm just moving this term over, right? And then this is added with b hat c hat f. And I just realized, my apologies, this is supposed to be a subtraction, because the subtraction here carries over to both, like that. So plus b hat c hat f minus c hat b hat f, in which case this is just equal to the commutator a hat c hat added with the commutator b hat c hat. All right, that's easy enough. Next one, the commutator of a hat b hat with c hat. If we extend this one out fully, this gives us a hat b hat c hat acting on f minus c hat a hat b hat acting on f. And unlike the first problem here, we can't really just expand this out further, so it's not really clear what else to do from this point. So instead of doing that, let's try to work from reverse and start with what it's supposed to equal and see if we can work our way back to this. So if we do it that way, well, a hat b hat c hat commutator plus a hat c hat commutator and then b hat like this, well, this is equal to a hat acting on b hat c hat minus c hat b hat f, and we're adding a hat c hat minus c hat a hat b hat acting on f. Expand these out because once again operators are distributive, so a hat b hat c hat minus a hat c hat b hat. Let's get the f's out as well, I forgot to include those. And over here, plus a hat c hat b hat f minus c hat a hat b hat f. So ACB, these two terms cancel. What we're left with is a hat b hat c hat f minus c hat a hat b hat f. And if we look, this is exactly the same as this, right? A hat b hat c hat minus c hat a hat b hat. Therefore, this is equal to a hat b hat commutated with c hat, like that. And that's part A. So now let's do part B. Okay, part B is between two actual legitimate operators now, x to the power of n and p hat, and we want to show that their commutator is equal to this. So let's write this out fully. X to the n p hat commutator is going to give us x to the n times p hat of whatever function we're dealing with minus p hat x to the n times whatever function we're dealing with. X operator is just x, right? Therefore, x to the power of n is just going to give us x to the power of n as well as an operator. P hat is our momentum operator. It's negative I h bar d by dx. So if we write this out fully, this commutator is going to equal x to the n times negative I h bar d by dx of f minus, the minus here with the minus and the p hat cancels out to make a positive, so plus I h bar d by dx of the entire term xn times f, like that. Let's rewrite this on the front. Negative I h bar x to the n df by dx plus I h bar. Here we're going to use product rule or chain rule, whatever you want to call it. So this is going to give us dx to the n, or I guess let's just derive it straight up. So this is going to give us nx to the power of n minus 1, box prime times triangle, f, plus triangle prime times box, so x to the n df by dx, like that. Writing this out further, negative I h bar x to the power of n df by dx plus I h bar times n x to the power of n minus 1 times f plus I h bar x to the power of n df by dx, in which case this term and this term both cancel out, leaving us with this middle term I h bar n x to the power of n minus 1 times f, which is exactly what this is. And just like that, we are done with part B, because remember, this f is an arbitrary function. We can just leave it out of the commutator, right? So yeah, now let's move on to part C. Okay, part C is basically the exact same thing as part B, but with a bunch of fancy vocabulary. So show more generally that the commutator of any function of x with respect to p hat is going to equal I h bar df by dx for any function f of x that emits a Taylor series expansion. What this means is that f of x is essentially a smooth function. So the requirement for something to be able to be Taylor expanded is that it has to be smooth. And what smooth means is that it's infinitely differentiable. So what this is basically saying is that, okay, df by dx is guaranteed to exist because that's the only way for a function to be smooth and therefore expandable via a Taylor series. So let's just write this out. The commutator between f of x and p hat is going to equal f of x, p hat acting on big F, minus p hat f of x acting on f, in which case this is going to give us negative I h bar f of x df by dx, like that, and then plus I h bar d by dx of the whole term f of x big F, like that. This inner term is going to, by chain rule, go to df by dx times f plus f of x df dx, right? So negative I h bar f of x df by dx plus I h bar df by dx times big F plus I h bar f of x df by dx, like that. In which case this term cancels with this term and you get I h bar df by dx big F, in which case, you know, this is just our function that we're acting the commutator on, or the operator on, so it just goes away, in which case this is our commutator term I h bar df by dx, which is exactly what this is, and with that we are done with part C. Okay, part D is asking us to show that for a simple harmonic oscillator, the Hamiltonian and the ladder operator commutes as plus minus h bar m, or h bar omega a hat plus minus, and our hint is to use equation 2.54. So 2.54 was the equation that related the Hamiltonian to the ladder states, and it basically says h hat is equal to h bar times omega a hat minus a hat plus minus 1/2. So if we write out the commutator fully, this is going to be h hat a hat plus minus minus a hat plus minus h hat. So this is equal to h bar omega a hat minus a hat plus, and I'm just going to include the a hat plus minus via distributive property, minus 1/2 a hat plus minus, and then minus h bar omega a hat plus minus a hat minus a hat plus minus 1/2 a hat plus minus. or actually, yes, okay. I don't think I'm missing any signs, right? Minus h bar omega, yeah, a hat plus minus goes in like that, yeah, okay. Sorry about that. And now, let's combine these terms, h bar omega, a hat minus a hat plus a hat plus minus, minus 1/2 a hat plus minus, minus a hat plus minus a hat minus a hat plus 1/2 a hat plus minus, in which case this term and this term cancels out, so what we're left with is h bar times omega, and then a hat minus a hat plus a hat plus minus, minus a hat plus minus a hat minus a hat plus, like this. So at this point, we're kind of stuck because we're not sure how to get to this, right? Because this is obviously a very different thing compared to what this is, but the solution to this is actually to recognize that back in chapter 2, one of the other things we noted was that ladder operators themselves are also not commutative, and they actually also in fact have commutators. And in chapter 2, what we found was that the commutators were that the commutator of a hat minus a hat plus was equal to +1, and that the commutator of a hat plus a hat minus was equal to -1. So in that case, we can look at the a hat plus and a hat minus terms separately. So what I'm going to say is, okay, h hat a hat minus, this is going to give us h bar omega, a hat minus a hat plus a hat minus, minus a hat minus a hat minus a hat plus, in which case what I can do now is I can recognize, okay, there's an a hat minus at the front in both cases. I can factor that out via distributive property, h bar omega a hat minus a hat plus a hat minus, minus a hat minus a hat plus, which, you know, this is just the commutator of a hat plus a hat minus, which is just equal to -1. So therefore this is equal to negative h bar omega a hat minus. Similarly, if I do the commutator of h hat with a hat plus, this is going to give me h bar omega a hat minus a hat plus a hat plus, minus a hat plus a hat minus a hat plus, in which case these two terms are the same, so I can distribute that out to the right. This is going to give me h bar omega a hat minus a hat plus, minus a hat plus a hat minus, and then a hat plus, in which case this term right here is going to be the commutator of a hat minus and a hat plus, which is 1. So this is therefore equal to h bar omega a hat plus. And if we look up here, right, whoops, I think I just cut it by accident. So a hat, the commutator of h hat with a hat plus minus is plus minus h bar omega a hat plus minus. So if it's a plus, it's plus h bar omega a hat plus, and if it's minus, then it's minus h bar omega a hat minus. So therefore we've proved this generally, and we are done with this problem.